Ladies and gentlemen, welcome to video lecture number 12 in a series of video lectures that are companions to the book The Fivefold Sun, which was filed at the Bibliothèque Nationale de France in late 2017. We are now on November 17, 2018, about a year later. Video 12 focuses on the first part of the investigation of latitudinal evidence for or against icosahedral symmetry in the solar ball. In this video, we now discuss high latitude evidence and will introduce the notion of a polar cone. In the contents of Part 2, we are at midway through Part 2 in Section 7, High Latitude Evidence. The contents of this video start with a consideration of high latitude, large-scale phenomenology in the solar ball. Then we go through the few most important accepted notions in solar physics with respect to this high latitude phenomenology. To start with, we now introduce the notion of polar caps from a magnetic point of view in solar phenomenology. The polar caps are the region of the Sun in which is supposed to be enclosed the unipolar magnetic field with north polarity at the North Pole and with south polarity at the South Pole. Of course, the polarity is reversed after 11 years during solar maximum at the poles. The issue at hand is where do the unipolar regions end in latitude? What are the accepted notions with respect of this boundary? In the 1950s, at Mount Wilson Observatory in California were first fully observed and described the solar fields, the background solar field with only a few Gauss intensity. Babcock, the son, and Babcock, the father, were important authors in this respect, and they found from consideration of the fields in the Sun at the time of their work in the 50s that the unipolar field was ending about 55 degrees in latitude. However, it was realized later that, of course, this boundary may be dependent on the strength of the cycle and of the variations with time of the typical intensity of the polar fields. However, there is to date no consideration in solar physics literature of a statistically representative latitude over a time average for this quantity. If we turn now to accepted notions with respect to the Sun's differential rotation profile in the high latitudes, which is perhaps the second most important parameter for an investigation of high latitude phenomenology, we are in solar physics still using mostly continuous differential equations to describe the differential rotation profile across latitudes. Whereas we saw in Part 1, when we investigated this differential rotation to set the slowest and the fastest rotation values in the solar ball, that in the high latitudes, which are the least well-known latitudes, there may be some discontinuities. In the 2000s, in the early early years of the current century, it was realized that the expected theoretical profile for solar rotation across the solar radius and varying with latitude was not represented by the geometry that was theoretically predicted with Taylor columns as expected from the terrestrial case. The so-called banana profile was introduced to try to account for what was seen in helioseismologically defined solar rotation profiles in depth and latitude. In this quote paper, which is in fact the Fivefold Sun as a book encompassing 15 volumes, what was found in this part of the investigation is, as far as a characteristic latitude boundary for unipolar solar fields, was that this value since 1878 probably was about 58 degree latitude. Obviously, only the minimum epochs are the right time to investigate the polar fields, which are supposed to peak at or near sunspot minimum epoch. And at the minimum of 1996, the latitude boundary for the unipolar region was about 62 or 62.5 degrees, which of course is at odds with the accepted canonical value set in the 50s on just one minimum of about 55 degrees. And based on this finding, we arrive in the next section for the interval since 1878, when the necessary data were first gathered, to a range of 57-58 degrees in latitude, or maybe this is really has really been 59 to 61 degrees in latitude for the reconstructed secular latitude of the polar boundary, be it a mean latitude or a median latitude. So we conclude in the book The Fivefold Sun, after this long meta-analysis of most of all of the literature citations that could be found, that the secular characteristic value is about 58 plus or minus 2 degree latitude. We now turn to the other main issue of high latitude phenomenology, differential rotation and its profile in depth and versus the solar radius. What is found in the Fivefold Sun project is that there is in the solar rotation profile a rotation on cones, as is already accepted in this century in solar physics literature. More specifically, the rotation is parallel to a polar cone that we are now going to introduce. First of all, there is evidence of a dividing line in the latitudinal solar rotation profile. This dividing line at a high latitude separates, as it is suggested in the Fivefold Sun as a book, that there are two regimes of the solar differential rotation, thus separated by this dividing line. This is, of course, entirely based on helioseismologic measurements that have been available in only since the very late 20th century. We first defined the notion of a permanent polar cap boundary at the solar surface. Because if we go back to the polar cap boundary of the unipolar fields, of course it can be defined only intermittently when there are such polar fields about solar minimum epoch. During solar maximum and a few years before and after, it is really difficult to to define a unipolar region. But now, with the help of the rotation profile, we will try to arrive at a permanent, the definition and the determination of a permanent polar cap boundary. In section 7.2.2 of the book, it is found that this dividing line is near 58 degrees again, and that at this latitude, near the surface of the solar ball, angular velocity is close to the average of the slowest and fastest angular velocities in the solar ball, as determined also in part 1 of the Fivefold Sun. So this location in latitude is interesting because it divides the solar ball in a high latitude region with slow velocity, slower than average, and a lower latitude region with faster than average velocity. It is then found this more central notion in what is going to be suggested of the inclination of isotax in the rotation profiles of the Sun. And it is suggested that the inclination of isotax in this profile is minimal at a certain unique latitude. When you look at the isotax in the solar rotation profile that are located at lower latitudes, what is found is that these isotax are parallel to the 58-degree isotax. Here you see a hand-drawn cartoon of the solar rotation profile in a quarter of the solar disk, as is canonical. The vertical line is the solar rotation axis, and the horizontal line is in the solar equatorial plane. You see these straight lines. There are 20 of them that are drawn from 0.655 photospheric radius to 0.93 photospheric radius. They are the 20 segments in the published isotax and solar rotation profiles that include a straight segment. Here I drew only the straight segments in this isotax. And these are superpositions of all of the isotax that I could find in the literature that I superposed to the same scale on a single chart. And then from this chart, I extracted these 20 segments. Closer to the axis, there are not any such straight segments, and closer to the equator, there are also not any such straight segments. So what do we see? There is an isotax at 58-degree latitude that is approximately radial. So the radial line at 58 degrees is, according to this bit of data, it would be the unique radial line on which a solar rotation profile isotax is aligned as a straight segment. We conclude that the 58-degree radial line seems to impact on the rest of the rotation profile because it seems perhaps to be imposing a certain inclination onto the rest of the solar rotation. If we now come back to the 2D projection of our 3D model for an icosahedral arrangement in the solar ball, we realize that the 58-degree latitude is the central angle boundary here of a polar ball. This is because the central angle from one side to the other of a polar ball, as for any other ball in this arrangement, is the icosahedral fivefold central angle of 63 degrees. Hence, half of it is half of 63 degrees, and the rest here is 58.28 degree latitude. So this is what would correspond with our icosahedral arrangement. If we now look to the 3D model introduced in video 8, the 3D model now has a new feature. It includes a cone. This cone reaches to the center of the sun, but is truncated because it is going through another region between the center of the sun and the polar ball, which is the central core. So this cone has a slope of 58 degrees. At least this model tries to approximate this slope. And so is defined within our 12-ball arrangement a conical region which we can now propose contains the unipolar solar fields. We now can combine this geometry of the 58-degree latitude isotac, defining this polar cone, with the idealized here in orange color inclination of isotacs in the lower latitudes. If we now try to reflect on the direction of 3D changes in solar rotation, in view of the findings reported here and of the interpretation, the idealized interpretation that was just suggested in terms of the angle geometry in the suggested fivefold arrangement for the solar ball. First of all, we find 90-degree rotations in isotac orientation. Versus the radial line, there is a rotation of 90 degrees from pole to the 58-degree latitude inside the polar ball cone. Versus the rotation axis of the sun, there is a rotation of 90 degrees from rotation pole to equatorial plane. If we now turn to increment an incremental trend in solar rotation in angular velocity with latitude and with radius, the direction is from the rotation pole, where there is slowest rotation, as we found in part 1, and along a line, which in fact defines a cone, which is normal to the radial line at 58-degree latitude. We could call this a sort of anticone. It is inclined as a result at 58 degrees versus the solar rotation axis. Finally, the increment trend in solar angular velocity is steepest in the region within the polar ball's cone. There is median steepness in the gradient of solar angular velocity from the cone to the lower latitudes, and near the equator the gradient is quasi-nil. There is stable angular velocity. This seems to be a region which is located just beyond the intersect of the normal line that we defined with the photospheric surface. These are the icosahedral angles to be checked as defined in an earlier video, and you can see that we have encountered in the current discussion in this video 3 of the 6 main angles: the fivefold vertex central angle of 63 degrees, it's half of 31.7 degrees, and the 58.28 degree angle. So what is the conclusion of the consideration of radial evidence and high latitude evidence with which we dealt in the last 2 videos? As far as the radial evidence is concerned, in video 11 we found that the length of the axial dipole coincides with the solid body vertex at 0.655 radius fraction in the Sun. We found that there is such a thing as an effective magnetic pole in each polar region of the Sun. It is also at 0.655 radius fraction, coincides with the centers of the polar balls as defined in our suggested icosahedral arrangement. And now in video 12, considering high latitude evidence, we find that the unipolar field of the Sun is wrapped in a cone about each polar ball, contained in a conical, above a conical line at 58 degree latitude approximately. We also found that in the lower latitudes, rotation happens in cones that are parallel to this polar cone. Is this rotation on cones in the lower latitudes related to the solar toroidal magnetic field? This is what we will investigate in the next videos. This is, ladies and gentlemen, the end of video 12. I thank you for your attention.